So in this section, we're going to talk about one type of matrix factorization, so-called LU factorization. So suppose that we want to solve the set of equations where A is the same matrix for each equations. Then if A is invertible, then we can certainly solve for X by multiplying the inverse matrix of A. So for example, for the first one, if we multiply A inverse for the both sides, then that gives you this equals to A inverse times B. In other words, X becomes A inverse times B sub 1. So the solutions are A inverse times B sub 1 and A inverse times B sub 2 and so on until A inverse times B sub n. But we cannot use this trick if A is not invertible. And in that case, we need to REF the augmented matrix, but there are lots of calculations involved. So to reduce the number of operations you do, we're going to use LU factorization method here. So if you can factor out A into L times U, where L is the lower triangular matrix and U is the upper triangular matrix, then we can reduce the number of operations you do, or the number of steps you do to solve the equation. So basically, the lower triangular matrix means, well, we have 1 on the diagonal entries and zeros in the upper triangular part. And for the upper triangular matrix, you have zeros in the lower triangular part. So for example, if A is given by this 4 by 5 matrix, then one can decompose this into a lower triangular matrix L and the upper triangular matrix U. And here you can see that, well, we have 1s in the diagonal entries and zeros on the upper triangular part. And for U, we have zeros on the lower triangular part. So you can ask a natural question that why we really do these things. And this method really helps you to calculate things more efficient. So suppose that A is given by 4 by 4 matrix, and B is the vector, and L is a lower triangular matrix, and U is an upper triangular matrix. Then note that if you multiply L by U, then you will restore the given matrix A, and you want to check it really true by yourself. But in this example, we're going to assume that A can be factored into L times U. Now, we're going to use this factorization to solve the non-homogeneous matrix equation. So, solving for X means you want to find X in R4 such that, so this is your R4, and you have a point here. And if you multiply A to X, then that should map X into the point B. But here, if A equals to L times U, then AX equals to B is equivalent to have L times UX equals to B. So we can think of this as first multiply by U to have U times X in R4, and then multiply by L to get to the point B. So let's say U times X to be Y. Then we're going to solve two different equations. So the first one is L times Y equals to B. And then once you solve for Y, then we can get X by solving UX equals to Y. So let's consider the augmented matrix. So for the first one, augmented matrix made by L and B is given by 1, 0, 0, 0, 12, 3, 1, 0, 0, 0, negative 1, 0, 1, 0, and negative 6, negative 3, 4, negative 2, 1, and 5. If you RREF this matrix, then you get 1, 0, 0, 0, 12, 0, 1, 0, 0, negative 36, 0, 0, 1, 0, 6, 0, 0, 0, 1, 197. And now we know that this column is the vector y. And to solve for x, we have to consider the augmented matrix made of u and y, which is given by 1, -2, -2, -3, and 12, 0, -3, 6, 0, and 0, 0, 0, 2, 4, and -6, 0, 0, 0, 1, 5. And again, if you RREF this matrix, then you get 1, 0, 0, 0, -17 and 19, 0, 1, 0, 0, -770, 0, 0, 1, 0, -391, 0, 0, 0, 1, 197. And now we got the solution x. But here, we're interested in the number of calculation we did. If you look at the first step over here, then we need to first reduce the first column. So we have to multiply some number and add to each rows. And once you do that, you do the same thing for the second column. And again, you do this for the third column. So we can tell that, well, the number of steps is, so we have to multiply 6 times, and we have to add each rows by 6 times. And for the second case, we need to divide some numbers into pivot position to make it equals to 1. And you multiply and add each rows to cancel out all these numbers in the columns. So we need 6 multiplication and 6 addition. Overall, we need in total of 6 plus 6 plus 4 plus 6 plus 6, which is 28 number of operations. And if you compare this with the usual row reduction, well, it actually takes 62 number of operations. So this tells you using the LU factorization is more efficient than the usual row reduction method. So we want to find an algorithm to make A into L times U. So first of all, to get U, the upper triangular matrix, we're going to reduce A to row echelon form using only row operation that adds a multiple of one row to another row below it. So here, suppose that you got U by doing this kind of elementary row operation, then these elementary matrices are all lower triangular matrices, which means their product is also lower triangular matrix. And once you got U, so if you multiply by the inverse matrix of that one, then this gives you A equals to EP dot 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 E2 E1 whole inverse times U, and this one is the lower triangular matrix. So here, if you get U by taking a sequence of row operation, say EP through E1, then this operation sends L into the identity matrix. So let's see how we get L and U by working on the given matrix here. So first of all, to find U, we have to take REF of the augmented matrix A and I. So the augmented matrix is given by 2, 4, -1, 5, -2, 1, 0, 0, 0, -4, -5, 3, -8, 1, 0, 1, 0, 0, and 2, -5, -4, 1, 8, 0, 0, 1, 0, -6, 0, 7, -3, 1, 0, 0, 0, 1. So here, the only allowed operation is to multiply some number on a row and then add that row to the row below it. So for example, you multiply by 2 to the top one and add that to the second one, and you multiply by -1 and then add that to the third one, and you multiply by 3 to add that to the last one. Then you get a equivalent matrix, which is given by 2, 4, -1, 5, -2, 1, 0, 0, 0, 0, 3, 1, 2, -3, 2, 1, 0, 0, 0, -9, -3, -4, and 10, -1, 0, 1, 0, 0, 12, 4, 12, and -5, 3, 0, 0, 1. And now what you can do is you multiply some number on the second row, like for example, multiply by 3 to add this to the third one, and multiply by 4 or -4 to add this to the last row. Then this gives you 2, 4, -1, 5, -2, and 1, 0, 0, 0. And I guess 0, 3, 1, 2, -3, 2, 1, 0, 0. And we get 0, 0, 0, 2, 1, and 5, 3, 1, 0, and 0, 0, 0, 4, 7, -5, -4, 0, 1. So here the point is we can go from top to bottom, but we cannot go from the bottom to top. And here we have a upper triangular matrix over here, which you get U. And the thing on the right equals to the inverse of L. So to get L, we need to find the inverse matrix of the inverse matrix of L. So that means you want to find the reduced row echelon form for this augmented matrix. So here, this is given by 1, 0, 0, 0, 2, 1, 0, 0, 5, 3, 1, 0, and the -5, -4, 0, 1. And the right side, we have the identity matrix. And we can reduce this by multiplying. So you want to multiply by -2 on the first row and add this to the second row. And similarly, you want to multiply by -5 for the third one and +5 for the last one. Then this gives you 1, 0, 0, 0 on the first column. And if you do all the calculation, you get 0, 0, 0, 1, 0, 0, 3, 1, 0, -4, 0, 1. And on the right side, we have 1, 0, 0, 0, -2, 1, 0, 0, -5, 0, 1, 0, 5, 0, 0, 1. And you do the same thing for the second column. Then this gives you the identity matrix on the left. And on the right, we get 1, 0, 0, 0, -2, 1, 0, 0, 1, -3, 1, 0, -3, 4, 0, 1. So this is the identity matrix. And you can see here that we have 1s on the diagonal entries and 0s on the upper triangular entries. So that one corresponds to the matrix L. So you can really check whether L times U really gives you A. So for example, calculate the product of L and U and check by yourself that you really get A if you take the product of these two matrices.